Alright guys, we're going to do chapter 6.2 and 6.3 together. I'm actually going to do chapter 6.3 first, and then I'm going to do 6.2 right after that. And hopefully you'll kind of see why. But we've really just got a whole bunch of examples that we're going to go through to kind of get you in the mode of how to solve and how to work with these problems. That's kind of the goal here. So hopefully you'll be able to do that after we're done with the rest of this chapter 6. And then you'll be good for the semester. So I'm just going to start right off with an example. Example 1 says, if p of x equals x minus 1 times x plus 2 times x plus 5, find. A says the zeros of p of x, B says the solutions of p of x equals 0, and C says the x-intercepts of the graph of y equals p of x. Okay? Now, what I want you to notice here before we get deep into solving this problem, because it's not a really difficult problem, but I want you to know, or to notice, that A, B, and C are all asking for the same thing. If we go to find the zeros of p of x, that means we find when p of x is 0, which is exactly what B is asking us to do. Find when p of x is 0. C says the x-intercepts of y equals p of x. Well, you have an x-intercept when y is 0. So we're really looking for 0 equals p of x, which is what we're looking for in B, which is also what we're looking for in A. So any of these questions are essentially asking for the same thing. So don't let that mess you up. I could ask you any of those questions. I'm asking you to do the same thing. Alright, so let's take it to the board real quick, solve it out. It's a really simple problem, and we'll get right back to example 2. Alright, so this is what we're looking to solve for A, B, and C. We're solving the same thing because the answer's T. To the first one will be the answer to all the rest of them as well. So really all we're looking to do is set this equal to 0 and solve for x. Okay, so in order to do that, anything that makes this whole thing 0 will be an answer. So if this piece is 0, this piece is 0, or this piece is 0, then we're going to get an answer, because 0 times anything is 0. So if any of these pieces are 0, then we're going to have the solution to the equation. So I'm going to set them all equal to 0. And then I'm going to solve each of them individually. So if I solve here, looks like x equals 1. Here, looks like x equals negative 2. And here, looks like x equals negative 5. So, the solution would be 1, negative 2, negative 5. If you wanted to write it as an ordered pair, 1 comma 0, negative 2 comma 0, and negative 5 comma 0. That's simple, and that will be the answer to all three, A, B, and C. So example 2, a box is to be formed by cutting a square of x inches per side from each corner of a square piece of cardboard. That is 24 inches on each side, and folding up the sides. This will give a box whose height is x inches with a length of each side of the bottom 2 times less than the original length of the cardboard. Using V, which is volume, equals length times width times height, the volume of the box is given by the volume equals, and you see it right there, where x is the length of the side of the square that is cut out. Use the factors of V to find the values of x that will give a volume of 0. Okay, so B says graph the function that gives the volume as a function of the sides of the square that is cut out over an x interval that includes the x values found in part A. And C says what input values make sense for this problem. D says graph the function using input values that make sense for the problem. And E says use technology to determine the size of the square that should be cut out for the maximum volume. Alright, so let's go about doing this piece by piece. I'm going to take A to the board. The first thing that I really like to do with this before we get into A is kind of show people how this box is constructed. Because the construction of the box in the word problem really messes with some people. So essentially, if you have a flat sheet of paper like this, right, if you want to make a box, you got to cut out squares on each corner so that you can fold it up into a box. Okay, so if you cut a square out at each corner, the piece that you cut out, this length on this piece is x, right? Okay, so that when you cut it out and you fold it up, what happens is the length here from here to here is actually the new length of your side. And that length is going to be 24 minus that 2x for all sides. So this new length is 24 minus these 2x's. So that'd be 24 minus 2x. 24 minus 2x. And 24 minus 2x. Okay. So this is your length. Your new length is 24 minus 2x. And if you're looking at the volume formula, length times width times height. Oops. Write my h correctly. And what you get is 24 minus 2x for your length. Your width is on this side. It's the same thing, 24 minus 2x. Now the height is what really kind of messes with people. When I fold this up, so if I take this piece and fold it up, it's only going to be a height of x. So x is your height. And that's how they get that formula. The reason I show this to you is in case you ever have to do it again. So if I take something like this, right? If it was laid flat, right? If it was laid flat, it would have those square pieces missing on the corner. Alright? It's hard to believe me when I say that, but it really would. If you want to, you could do it with a plain piece of notebook paper. You could take one. I'm trying to be a little extra here. You could take a piece of notebook paper. Let's see, I do have a pair of scissors here. You could cut out squares on each corner, and I'm not measuring this out to be precise, so it's not going to be exact, but I'm going to make it as close as I can. Okay, so I've cut out my squares on each corner, right? So it's almost just like this. Now if I fold it here, fold it here. Like I said, it's not exact. This is very rough. Fold it there. And I fold it here. What happens is if I go to make my box like that, this length that I cut out right here, when it was originally flat, that square that I cut out there, it is now folded up to be my height, if you can see that. So here is your very not so perfect box, right? And to find the volume of a box, you go length times width times this height that you folded it up. That's essentially how this is working here. To get on to part A, if we want to find what gives a volume of 0, we take the formula, we set it equal to 0. Each of these individual pieces, any of those individual pieces equals 0, and we're going to have a volume of 0. So 0 equals 24 minus 2x. I'm only going to write that one time, even though there's two of them, because if I solve it, it's going to give me the same thing. And then 0 equals x, right? So we already have one answer. That was pretty straightforward. If I solve for this one, I get 2x equals 24. So x equals 12. So if x equals 12, right, I'm going to have a volume of 0. Or if x equals 0, I'm going to have a volume of 0. And that kind of makes sense, right? Okay. So if I cut out over here, originally my length's 24. If I cut out 12 inches here, and I cut out 12 inches here, I've literally cut the whole side off, right? So now it's still just a flat piece of paper. Okay. If I don't cut anything off here, so my x here is 0. If I don't cut anything off, it stays a flat sheet of paper. It doesn't have a volume. Has an area, not a volume. So that makes a whole lot of sense. You can't cut off any more than half of this and expect to get something. Okay? So that's the answer to A. If we look at B, it says graph the function that gives the volume of the function of the side of the square that is cut out over an x interval that includes the x values found in part A. So the x values found in part A were 0 and 12, so our interval needs to include 0 and 12. So if we come over here to our calculator, right, I've kind of already done it, but you need to type your equation in first. So type your equation in the y1, pause here if you need more time to type it in. And then what we're going to do, I'll start from scratch. If you want to, you can zoom standard. But when you zoom standard, one, it doesn't give you a good view, and two, in your window, it doesn't include that 12 part. Okay, so there's no need to really go below 0 for X. The reason being is I can't cut out a negative piece of paper, right? I can only cut out a positive piece of paper. So if you start here at 0, that makes sense. And you could go to 12, but I'm going to actually go to 24 because that's the total length of our side. Alright, if you graph that, it looks a little better, but it's still kind of squirrely. If you hit zoom fit, which is zoom 0, you get a pretty decent looking little graph right here. Okay, so going back to the question, it says graph the function. We've done that. C says what input values make sense for this problem. That is, actually result in a box. So if we look at this, right, the input values that make sense, that actually form a box, are from 0 to 12. Okay, so like I said before and explained on the board, if you cut any more than 12 off of a side from both directions, you're literally cutting off the whole side. Okay, so you really can cut no more than 12 off of each side. If you cut more than 12 off of each side, that really doesn't make sense either. How can you cut 13 off of one side and 13 off of another side when the whole side only measures 24 inches, right? So the only values that really make sense are from 0 to 12. So I can write that in. Let's see, add notes. Let's go on and do that. 0 to 12. Okay. D says graph the function using the input values that make sense for the problem. So it essentially wants us to come over here and adjust our window. So instead of from 0 to 24, let's go to 0 to 12. Hit graph. There it is. Those are the values that make sense. If you want to make it look a little prettier, you can do zoom fit after that, and it'll make it look a little bit better on your screen. Completely up to you. Okay, we've done that. E says use technology to determine the size of the square that should be cut out to give the maximum volume. Okay, so if I come over here to get the maximum volume, what I should be able to do is do second calc. Okay, and then I should be able to do maximum and just find the maximum. Okay, I'm gonna go left, hit enter. I'm gonna go right, hit enter, and then I'm gonna guess about where it's at, because Y is our volume here. So our maximum volume is gonna lie at X equals 4, and we're gonna have a volume of 1024. So we'll answer our question. Max should be 4, comma 1024. Right? Okay, so that's pretty much it. Okay, use technology to determine the size of the square that should be cut out to give the maximum volume. Okay, so 4 is the size of the square. So the real answer you'd be looking for here would be 4. So the size of the square here, that's your 4. The maximum volume, like I said, if you wanted to indicate that as well, would be that 1024. And it's that simple. Example 3 says the amount of Y of photosynthesis that takes place in a certain plant depends on the intensity X of the light in lumens present. According to the function, Y equals 120x squared minus 20x to the third, the model is valid for non-negative X values that produce a positive amount of photosynthesis. Okay, so obviously X here can only be non-negative values. You can't have a negative amount of light and expect to produce photosynthesis. Okay, A says graph this function with the viewing window large enough to see 2 turning points. B says use factoring to find the x-intercepts of the graph. And C says what non-negative values of x will give positive photosynthesis. Okay, let's graph it first. 120x squared minus 20x to the third. So 120x squared minus 20x to the third Alright, I'm going to zoom standard, even though it's probably going to do a terrible job. I think I did zoom fit. Zoom standard. Okay. I'm really hitting the wrong buttons here. Zoom standard, number 6. Okay, doesn't really do that great of a job. But what I do know is that if I'm looking at it, right, if I'm looking at it here, looks like I have a minimum right here, almost at 0, and then it does come up to appear to be a max right here at about 6. So I'm going to do window, because I do want to see 2 turning points. I'm going to do window from maybe -3 to, let's do an 8. We'll graph that, right? We don't need, also, we don't need Y really here to be any different than 0, right? We're not going to go below negative photosynthesis. That doesn't make any sense. That clears it up a little bit as well. If you hit zoom fit after that, it does a really good job. Okay, you really, I know the zoom part doesn't come naturally. It takes a lot of practice. I've been doing this for a while, so might make it look a little easier than it should be. But that's a really good picture. You've got 2 turning points. You've got one here, you've got one there. Okay, so we've executed part A. B says use factoring to find x-intercepts of the graph. Okay, so we need to come over here, and I'm going to put this on the board, and we can use factoring to find the x-intercepts of the graph. Okay, now before I do that, since I'm already here at the computer, if you want to find the x-intercepts of the graph and be really easy about it, you could do second calc 0, and you can left bound, right bound, and find it, right? So little shortcut way to find it. I believe it hits right here at 0. That's what it looks like. Let's find out. Okay, evidently didn't. Okay, so let's see if we can find the other one. Second calc. Oops, second calc. Let's see, 0. Let's scroll over here to the left. I know it crosses the x-axis here. Maybe it doesn't actually cross it at 0. We'll see when we factor it as well. I'm pretty sure it does. Okay. Sometimes your calculator has a hard time when it's really close to 0 deciphering whether it actually does touch. But here we have a 0 at 6, 0. So we should at least be expecting to look for that one. Like I said, I believe if you look at the table, you can see at 0, 0 there is a point. So you do have a 0 at 0 as well. But I'm going to go on the board real quick, and I'm going to show you how to factor it out by hand. Find the real zeros by factoring. So I'm going to go ahead and set it equal to 0, but I'm going to go ahead and factor it as well. One of the things that I can pull out of here is obviously an x squared and a 20. So let's go ahead and do that. 0 equals 20 x squared. Okay. I pull a 20 out of here. I'm left with what, 6? I pull a 20x squared out of here. I'm just left with minus x. Right. Either one of these, if this term equals 0, the whole thing's 0. If this term equals 0, the whole thing's 0. So if I set 20x squared equal to 0, and I set 6 minus x equal to 0, I should be able to find my 2 zeros. Here, obviously, if x equals 0, it works. You can divide by 20. 0 divided by 20 is 0. Square root of 0 is 0. X is 0. Here, if x equals 6, is 0. So, there's your 2 answers. X equals 0, and x equals 6. Try to make a decent look at 0. Like I said, we can factor it by hand, we can find it on the calculator. Whatever your fancy is, just make sure you get the right answer. C says, what non-negative values of x will give positive photosynthesis? Okay. Alright, if I'm looking at the graph, obviously it makes sense from 0 to 6. Right? Because here we have positive photosynthesis. Here photosynthesis is negative. Here photosynthesis is positive, but we can't have a negative x value. So from 0 to 6. So, okay, we're looking at non-negative values of x. We've got 0 is less than or equal to x is less than or equal to 6. You can also give that an interval notation if you'd like. You can say from 0 to 6. That's fine. Make sure you use your brackets if you do that. And that would be the answer to example 3. We got a part D. Graph the function with a viewing window that contains only the values of x found in part C and non-negative values of y. Okay, little window exercise. We get windows, so we're going to go from 0 to 6, non-negative values of y. So y min, 0, y max, whatever that is, we'll leave it the same, and we'll graph it. And it does a really good job of graphing it. Okay, just like I said, an example on how to use your calculator a little bit more. Before it says the total cost of producing a product is given by the function c of x equals in thousands of dollars, where x is the number of hundreds of units produced. How many units must be produced to give a total cost of $45,000? Okay, so the easiest way to do this is to pull up your calculator, okay, and type this function in. I'm going to pull it over here to the right a little bit so I can actually see the function, type it in. So in y equals, I'm going to type x to the third minus 12x squared plus 3x plus 9. Okay, and then we want it to give a total cost of $45,000. I'm going to put that in y2. Okay, there it is. Now I'm going to do zoom fit, or you can do zoom standard first to kind of clear your preconceived stuff out. Okay, you can do zoom fit next, and it should show you both. Okay, it shows you both. Maybe it doesn't do a great job of it, but it does show you both. The zoom on this one is probably going to be a little more difficult. Obviously, you do want your window to go up to 45,000 because that's where your line's at. What you really need to do is extend your X. How long to extend your X is hard to say. I don't know. You definitely need it more than 100. If you want to try 1,000, you could try that. You can see it definitely hits by there. 1,000 is probably way too big. So if you want to scroll down and maybe fix it to 100, sometimes it's just a guessing game. 100 does a pretty good job. You can see that intersect right there. So that's what we're looking for. We're looking for where they intersect at. They intersect. We can find that. We can say, okay, our first curve is the blue curve, our other curve is the red curve. So I'm going to scroll over here so they intersect about right here. And it tells me they intersect at 40.018466 and 45,000. So at x equals about 40. So how many units must be produced to give a total cost of 45,000? Looks like about 40 units. Okay. Now you can solve that by hand if you wanted to. That's not a problem. I'm going to go to the board and show you how to solve that by hand real quick. Next thing I'm going to do is I'm going to review the root method. It says the real solutions of the equation x raised to the n equals c are found by taking the nth root of both sides. So x equals the nth root of c if n is odd, and x equals plus or minus the nth root of c if n is even, and c is greater than or equal to 0. So in example 5, we have exactly 3 examples that we can go over using the root method. So let's do it on the board. So A says x to the third equals 125. So with the root rule, we can essentially say x equals the third root of 125. You can double check it on your calculator if you want to. If you're not good with roots in your head, you could type the third root of 125, but it really just gives you 5. It's an odd root, so I don't have to put plus or minus, because negative 5 to the third is not going to give me positive 125, it's going to give me negative 125. So here, the only answer I have is x equals 5. Okay. B says 5x to the fourth equals 80. Obviously, you have to do your basic stuff here first. Divided by 5 gives you x to the fourth equals 80. Divided by 5, right? 80 divided by 5 is going to be what? It's going to be 16. So x to the fourth equals 16. Now, what I need to say is x equals the fourth root of 16. Alright. Now, you can type the fourth root of 16 in your calculator if you really want to, but it's pretty simple. 2 times 2 is 4, times 2 is 8, times 2 is 16. So x equals plus or minus 2. You really ought to have a plus or minus right there as well. It's an even root, So we have to have plus or minus, because negative 2 times negative 2 is positive 4, times negative 2 is negative 8, times negative 2 is positive 16. So negative 2 would work. 2 times 2 times 2 times 2 is 16. This last one, I'm going to divide by 4. I'm going to divide by 4. I have x squared equals 18 over 4. Alright, you can reduce that one or try to reduce that one if you want to. It'll actually be a little simpler, in my opinion, if you leave it like it is. Because what you can do at this point is I can say, okay, x equals plus or minus the square root of 18 over 4. Okay, and the cool thing about the square root is you could say plus or minus the square root of 18 over the square root of 4. Now, I know what the square root of 4 is. The square root of 4 is 2. Okay, if you would have simplified, you'd wound up with a square root of 2 in the denominator, and you would have to rationalize the denominator, and it would have got a little more difficult. Here, if you just left it, you wind up with 2 in the bottom. Square root of 18, we can reduce that. It's the same thing as the square root of 9 times 2, right? Square root of 9 is 3. So it's the same thing as 3 square root of 2 over 2. And you need to keep your plus and minuses in here. Don't lose track of those. So the answer would be plus or minus 3 square root 2 over 2 for part C. I know that one's a little difficult. Requires a good bit of algebra in there, but you can work it step by step and get there. Example 6 says the future value of $10,000 invested for 4 years at an interest rate R compounded annually is given by S equals 10,000 times 1 plus R to the fourth. Find the rate R as a percent for the future value, that is $14,641. Okay, so what we need here, we need to take this function here, right? Okay, it's already giving you the function, which is really nice. We're going to take this function, we need to essentially set it equal to this 14,641. The easy way, which is the way I'm going to show you, is just come over here to your calculator, right? So, I'm going to clear it out. I'm going to make it where I could actually see it. Okay, so our formula here is y equals, I'm going to clear the old formulas out here. Y equals 10,000. So I got 10,000 typed in times 1 plus r to the fourth. So x, close your parentheses and raise it to the fourth. Okay. Now in y2, I'm going to set it equal to 14,641. Okay. And you can see that's exactly what I did right here. Now I'm going to do zoom standard as I always do to start out with. It's obviously not going to give you the view that you want. Then I'm going to do zoom fit and really hope that it does a good job. Okay. That's not a terrible job. Okay. I can see that I have a line here, the red line. It kind of went a little too high on me. So what I'm going to do is I'm going to do zoom in. Okay. Just another method in trying to get there. I'm going to zoom down to where it looks like they kind of intersect down here. I'm going to hit enter. It did okay, but it really didn't do that good of a job. I can't really see much going on here. Okay. So what I'm going to do is I'm going to go back to zoom standard. Right. Okay. My window here, if you look at your y equals, obviously you want it to be around that 14,641 with your y. Okay. So in my window, I'm going to set it to 15,000 as my max, which is a little bit above what that is. Okay. If you graph that, obviously you can see where they intersect right there. It does a really simple job of it, just doing that one step. Okay. Now the thing is, if we come over here, right, and we're trying to logically answer this question, okay, and that's the big part of it, right? We want to find the rate as a percent for the future value. Okay, you're obviously not really going to be working in negative interest rates, so you don't need to worry about where they intersect over here. You really need to worry about positive interest rates. So if you want to adjust your window even, interest rate's not going to be negative. So if I set it equal to 0, that should be okay. If you want to get even better, you can say, okay, interest rate is going to be from 0 to 1, because 1 is 100%. And you can see that when you go from 0 to 1, and you want to see where it intersects at, you can see it really, really clear here. So now, if you want an extra look at it, interest rate goes from 0 to 1. Okay, so 0 to 100%. My y, okay, I really don't even need my y to be negative, so you could change that if you wanted to. But I maxed it out at 15,000 here because we wanted to figure out where they intersected with this 14,641. So I just went a little above that, and it gave it to me right there where it intersects. Now I'm going to use the function second calc intersect and figure out where they intersect at. Okay, so your first curve, your second curve, and then we're going to go over here and we're going to guess where they intersect at. Okay, they intersect at x equals 0.1. Okay, so 10%. So if you wanted to answer this, find the rate r as a percent for the future value of that, it would just be 10%. Okay, because it wants it as a percent. That'll be the answer to part 6. 7 says, using United Nations data from 1975 with projections to 2050, the size of China's labor pool, aged 15 to 59, can be modeled by the function, and it gives you the function here, where x is the number of years after 1970, and y represents the number of millions of people in this labor pool. Okay, we're going to use this model to estimate graphically the number or the years after 1970 when population is and will be 900 million. Okay, so what we need to do is we need to take this function, obviously put it in our calculator. So I'm going to do that first. So y equals, I'm going to drag it over here to the left so that I can put this in. I'm going to clear this out, clear that out, and type my new function in. So negative 0.0000487 x raised to the third, okay, minus 0.162 x squared plus 19.8 x plus 388. Is there anything else to it? Nope, that was it. And we want to see when it will be 900 million. Okay, the only thing you have to check when you do these millions is you got to make sure that millions is the one that you're starting with, and it is number of millions of people. We want it to be 900 million. So essentially what we're going to do for y2 is we're going to let y2 be 900. Okay, no need to type 900 million because it's already in millions. Okay, so what it looks like is this, right? So I've got the big overall function in my y1. I've got my y2 here typed in as 900 million, just 900 because millions is the units we're in. If you want to do a zoom standard, and then you could go back and you could do a zoom fit. Maybe it does a good job, maybe it doesn't. It doesn't look like they hit here. You could try to do a zoom out. It might work. I'm going to do a zoom out, see how well it works. I'm going to kind of go over here and then go in the middle of the two, hit enter one time. And it almost worked. If you wanted to, you could scoot over here. You could do maybe a zoom in. Like I said, the zoom part you really kind of got to play with. But it looks like I've got two intersections here. Okay, so it's really not a really good view. Okay, you can try to come back in here and you could try to play with it. Obviously 900 will probably need to be our cap on the upper side, right? How many years after 1970 will it reach that? Our initial size was 388. So if you come over here, you want to adjust your window, try to get there. Like I said, there's no need to really go too far over 900, so I'll do 950 as our max here. Min, I'm gonna just leave it what it is. My X max here and my X min, obviously you could do 0 all the way to, I don't know, 100 years after that. Let's see how well that does. Okay, that does a pretty good job, and you can still see it hits here in two locations. Okay, so you could do second calc intersect, and you could calculate both of them. Okay, so first curve, second curve, And then you really kind of got to get on it when you got two so close together. So get as close as you can to it. And it tells you they intersect at x equals 42.648118. Okay, that tells me about 43 years is the first one. Okay, so I'm going to go over here. It says 43 would be one of them. Okay, now I'm going to come over here. I'm going to find the second one. Second calc, intersect. Okay, first curve, second curve. Now you gotta make sure you kind of come over here and find that second one, get pretty close to it. And it'll tell you the second time they intersect is about 57. Okay, so 43 years after 1970 and 57 years after 1970 is when the population will be 900 million. Okay, sometimes you got to read through there and make sure they don't say like the first time it hits 19 or 900 million. I don't see anything like that in the problem. Okay, what you might want to do as well, depending on how I ask you to answer the question, is you might want to adjust accordingly, right? So essentially our first year is 1970, so 43 years after 1970, do you want to come over and be simple? 43 plus 1970, okay, gives you 2013. Okay, so in the year 2013, so 2013, that would correspond to that 43. What you'll also notice here though, okay, it says projections to 2050. Of course, we hadn't gone over 2050 with this 57, so I'm going to write that one as well. But you can come over here and you can do 57 plus 1970. Okay, that gives you 2027. So depending on how it wants the answer, you might have to convert it to the actual year. Alright, so when will the population be 900 million in both of these years? Okay, if you did want to look at your graph again, obviously 2050, 2050 would be what, 80 years after, if you do a simple trace, right? Makes sense that it gets kind of low after 80 years after, and a population probably not going to drop but so low. So the model might not be valid after 2050 is essentially what I'm saying, but it's projected to go up and then come back down. Okay, two answers I'd probably be looking for will be 2013 and 2027. Look at example 8. Example 8 says the number of international visitors to the United States in millions can be modeled by the equation, and it's got y equals, and it gives it to you, where x is the number of years after 1980. If the model remains accurate, when will the number of international visitors be 75 million? Okay, it is in millions, so we don't have to really worry about that. Really the biggest thing we're going to have to do is type this equation in. Okay, we've got to note that it's years after 1980, and we're going to type 75 into y2. So let's do that really quick. So I'm going to pull this over here so I can see it to type it. I'm going to do y equals, clear the old ones out. You can go ahead and put 75 into y2 if you want to. And then in y1, I'm going to type this big equation up top. 0.0101 x raised to the third minus 0.575 x squared plus 10.814 x, okay, minus 20.75, and I think there was more to it. Let's look and see. 753. Okay. Alright, so I've got it typed in y1. I've got 75 typed in y2. Like I said, I always start out with Zoom Standard. It doesn't always work. Here, obviously, it didn't. We obviously need our y to go up to at least 75. So I'm going to go to my window and automatically change that to my y max being 80. Okay. I'm going to zoom fit and see what happens when I do that. Okay, still doesn't show it. If I can go back in my problem here and look at it, I'm trying to see if there's anything that will associate it to how far I need to go out on the X side. Obviously, no need to go negative. Not really looking at negative years here. So I can start at year 0. I'll extend it, I don't know, maybe 50 years. See what happens. Graph that. I can see where they intersect there. Also, if you wanted to, you can hear why men started at 0. That might help you as well. You can see where they intersect up there. So what you can do is you can do second calc, intersect, highlight the first one, highlight the second one. Pardon the everybody sending me emails and making noises on my phone. And find the intersection point. So you intersect at x equals 33. Alright, Chris, get on out of here. 33.35 approximately, and y equals 75. So the answer you should be looking for is 33.35. If you want to round it to the nearest year, it'd be year 33. We have to know here, we look at it year 33, okay, number of years after 1980. So if you want to be really simple about it, 1980 plus 33. Oops. 1980 plus 33. So in the year 2013, that would be the answer we'd be looking for. Okay. And sometimes it will tell you to round up. And if it ever tells you to round up, what you're going to want to do is round it up to 2014. But the instructions will say if it wants you to round up or round appropriately. Here we rounded appropriately because the number we were looking at told us to round down. But sometimes it will ask you to round up. Example 9 says use the graph of the polynomial function to find the factorization of f of x. Okay. Now, I've got 3 of them here, so these can be kind of complicated. I might have to go back and forth from the calculator to the board, so just hang on tight. We're going to do A first, okay? And I'm going to do the calculator part of A first. So get ready for it. So I've typed the function in on my calculator. Now I'm going to do zoom standard. Okay. What I'm really concerned about here are my zeros. So I have a 0 here, here, and here. Okay. So when we find the prime factorization or the factorization of this f of x, like what we're looking for here, the zeros are very, very important. Essentially, we need to find them first. Okay. So that's what I've done. I've typed my equation here into my y1. All I've done is a standard zoom. If you notice, it's an x to the third. So the most zeros you can have are 3. I can see all 3 of them here. There's no need to do any extra zoom. Okay, so all I'm wanting to do now is calculate my zeros. Okay, so if I calculate my zeros, you can go left and right bound of all these, and sometimes that takes a bit. So if you want a left bound of this one, right bound of this one, and then guessed it, it would tell you that the first 0 is x equals -3, y equals 0. You could do that for all of these if you wanted to. Sometimes, though, to make it a little simpler, what you can do is go second table, and you can see the zeros. Okay, so here I can see that I have a 0 at -3, 0. I have a 0 at 1, 0, and I have a 0 at 4, 0. So there's my 3 zeros there, instead of having to do the second calc 3 times. So given those zeros, -3, 0, 1, 0, and 4, 0, I'm going to go to board now and show you what to do with those zeros. So essentially what we're going to do is we're going to take these zeros and kind of back solve and get the factorization of this original equation. Okay. So what I'm going to do is this would basically be set up as x equals -3, x equals 1, and x equals 4, right? So like I said, I'm going to back solve, so that's going to give me x plus 3 equals 0, x minus 1 equals 0, and x minus 4 equals 0. Okay, because when we go from a factorization to a 0, this is kind of the route we're going, so now we're kind of going backwards. So that essentially means that x plus 3 times x minus 1 times x minus 4 should equal 0, which should be the factorization of that up top. So let's see if we can show that. Okay. So what I'm going to do is FOIL this out and see if it equals this up top. If it does, then this is our answer. Okay, so what we have here, we'll do this times this is x squared. That'll be x times -1, which is negative x. 3 times x, which is 3x. Combine those two, you get a 2x. And then you get a -3 here. If you need more steps, by all means, take as many steps as you need to get the answer. I'm going to work through it kind of fast. We're at the very end of this semester. You should be able to do this kind of stuff. Okay, so I'm going to FOIL this one too. So x squared and x is x to the third. X squared and -4 is -4x squared. I'll change that to make it look more like a 4. Okay, now I need to do 2x times x, which is plus 2x squared. 2x times -4, which is -8x. -3 times x, which is -3x. -3 times 4, which is +12. Okay, if I simplify this, then I get x to the third. Combine those two, -2x squared. Combine those two, -11x, and then +12. And if I did everything right, that should match exactly what we have up top. So the factorization would be this piece right here. Okay, so you don't even necessarily need 0 on it, but that would be the factorization of that. This would be what we're looking for. Okay, so you can use your zeros to help you get there. This one's really simple. I didn't have a coefficient in front of my biggest x to the third term, so it made it really, really simple. If you have a coefficient up here, it can make things a little more tricky, and that's what I'm about to show you in part B. I'm looking at B here, and we're going to try to do this. Something to note with B is it has this coefficient of -2 in front of this x to the fourth. Okay, so that's going to make this problem a little more tricky. You can also note is that not only does it have this -2 in front of this x to the fourth, if I wanted to, I could take a -2 out of each one of these terms and still wind up with a perfect whole number. So I could take a -2 out of the 6, this -14, and this -12, and still wind up with whole numbers in all those cases. So I could divide each of these by -2 if I wanted to and essentially pull that -2 out. Okay, that's going to make it a little more complicated. I'm going to show you how to work with that. Okay, so what I'm going to do first is come over here to my calculator. I've got it all typed in. I'm going to go about it the same way. I'm going to do zoom. Let's do zoom standard. Okay, what it has here, if you see it, looks like it touches here, crosses here, and crosses here. Okay, let's see if we can go really simple. Go second table and see if it'll give us the zeros, and indeed it does. I've got a 0 here at -1, a 0 at 2, and a 0 at 3. Something I should also come back and notice, this is an x to the fourth. Okay, it can have as many as 4 zeros, but it doesn't have to have 4 zeros. Here it only has 3. Okay, so it has one at -1, 0, one at 2, 0, and one at 3, 0. And if I'm looking at the graph, the one it touches twice is at -1, 0. Now what that means, and you'll see it when I put it up on the board, what that means is that when it comes up here and touches, it kind of counts twice. And you'll kind of see what I mean when I put it up on the board. So let's go to the board real quick. Alright, so this is our original equation, and these are the 3 that we found here on the calculator. Okay, so what I need to do here, I need to do a few things. Okay, I've got this one highlighted because we said this one's going to happen twice. Okay, in this particular scenario, because we have 4, right? We got x to the fourth here, so there need to be 4 of them done. This is the one that happens twice because it touches. Okay. Something we also need to note here, I've got this -2 out front. Okay, that's important to note, especially because I can pull this -2 out of each one of these. So if I do that, -2, if I pull that out of this first one, leaves me with an x to the fourth. If I pull it out of the second one, it leaves me with -3x to the third. If I pull it out of the third one, it leaves me with a -3x squared. Here it leaves me with a +7x and a +6. Okay. Like I said, this -2 is very important, and you'll see why in just a second. So if I take it over here, back solve, I wind up with an x + 1 equals 0. I wind up with an x - 2 equals 0. And I wind up with an x - 3 equals 0. Okay. Now, just like we've been doing, I can combine those. So, like I said, this one needs to happen twice, so I can write it twice if I want to. So I get x plus 1 times x plus 1 times x minus 2 times x minus 3. And I'm going to take this red marker, because that negative 2 was able to be pulled out, I'm going to write it up front here. So this will wind up being your answer. I'm going to show you that it's right by factoring it all out. Okay? Or foiling it all out. So I'm going to leave that negative 2 out front the whole time until we get to the final answer. Negative 2. Okay. I'm going to do this first part. It'll give me an x squared plus 2x plus 1. The second part will give me an x squared, let's see, minus 5x, and then plus 6. Okay. Now, I'm going to FOIL those two together as well. Keep my negative 2 out front. X squared times x squared is x to the 4th. X squared times negative 5x is negative 5x to the 3rd. X squared times 6 will be plus 6x squared. 2x times 2x, or times x squared, is 2x to the 3rd. 2x times negative 5x is negative 10x squared. 2x times 6 will be plus 12x. Okay, and the last one's easy. It's just everything multiplied by 1. So x squared minus 5x plus 6. Obviously need to simplify that. Okay, so keep that negative 2 out front. X to the 4th cannot be combined with anything, so I'll just leave it alone. Okay, I need to combine this negative 5x to the 3rd and this 2x to the 3rd. That's going to give me a negative 3x to the 3rd. So we already took care of that one, that one, that one. Now, we need to combine these squareds. I got a 6x squared minus 10x squared. So that'll give me a negative 4x squared. And then I have an x squared here. It's going to be minus 3x squared. So I took care of that one, that one, that one. Now I've got a 12x minus a 5x, which is going to give me a plus 7x. And then I've got a plus 6. And by golly, this is the same thing as that, which means that this is the same thing as our original, and we have the factored version of it. So the answer that I would be looking for, the factored answer that I'd be looking for is this one. This is all just proof right here that it actually worked. Okay, so this would be your answer, part B. For this one, we're doing C, x to the 3rd minus x squared minus 4x plus 4. If you go to your calculator, type it all in, that's fine. You can do Zoom Standard, I think it's going to work fine for it. There it is. Hits it 3 places. It is a cubic function, therefore it'll have all its zeros, right? So we don't have to repeat any like we did in the last one. So I'm just going to look at the table, and the table shows me all 3 of them. I've got a negative 2 and a 0, a 1 and a 0, and a 2 and a 0. Simple enough. Okay. This one's really simple as well because it doesn't have a coefficient in front of this x to the 3rd, so we should be able to go about it just the same way we did the first one. So let's do it and try. Okay. So I'm going to write these on the board. So we got our original equation up top. We got our zeros right here to the left. What we can look at, so we back solve x plus 2, x minus 1, and x minus 2. Should be what it looks like, right? Okay. This is actually a really nifty one here. We anticipate it being x plus 2, x minus 1, x minus 2. Okay. I'm going to try to go about a little bit of a different way of proving this one. Let's see. So, I'm going to come over here, take this function, just rewrite it really quick. Okay. You can factor by grouping here a little bit. So, in this, the grouping I'm going to do is this and then that. So, I could pull an x squared out of this first grouping. If I did that, I'd be left with an x minus 1 here. Okay. I'm going to pull in this second grouping, right? In this second grouping, I'm going to pull out a negative 4. So negative 4, and that'll leave me with an x minus 1 here. And you'll remember with factor by grouping, essentially what we do is we keep this term, okay, and then multiply it by whatever's left. Okay. So, working on factoring by grouping right here. Now, I need to factor this piece as well. You should be able to factor that piece. It's just going to be x minus 2x plus 2. X times x is x squared. X times positive 2, x times negative 2 cancel each other out. Negative 2 times 2 is negative 4. Okay? So, what we get here is exactly what we got there. So, our answer here would just be that. 10 says the total cost function for a product is given by, where x is the number of units and c is the cost in hundreds of dollars. Use factoring by grouping to find the number of units that will give a cost of $120,000. Okay. Now, we're going to use factoring by grouping, but first thing we need to note here is that c is the cost in hundreds of dollars. Okay. Our hundreds place is right there. Okay. So our hundreds place is right there. So the c that we're going to use is going to wind up being 1,200. Okay. With that noted, I'm going to take it to the board and we're going to solve the rest of it by factoring by grouping. So I've got our function here on the board. We want to solve it by factoring by grouping, which means I need to get everything on the same side. So I'm going to go and subtract this 1,200 off on both sides, which gives me a 0 equals 3x to the third minus 6x squared minus 300x, and then we get 1,800 minus 1,200 is 600. Okay. Now, switch colors here. So, factor by grouping. I'm going to group this together. I'm going to group these together, right? Okay, 0 equals, what can I pull out of both of these? I can pull out a 3x squared, which will just leave me with an x in the first one, and it'll leave me with a negative 2 in the second one. Okay, you want this to be the same over here, so keep that in mind. What can I pull out of this to kind of make it look like this? I can pull out a negative 300. That'll leave me with an x minus 2 here, right? X minus 2 is what's in common. The rest of it I group together, so 3x squared minus 300. Easy enough, right? Now, if I want to, I can just solve it from here. Okay, let's do that. Say, okay, x minus 2 equals 0. 3x squared minus 300 equals 0. So x equals 2 is one answer. And let's see here. So if I add 300 to this side, add 300 to that side, 3x squared equals 300. Divide by 3. X squared equals 100, right? That means that x equals plus or minus the square root of 100, which is plus or minus 10, right? So we got three answers here. Our three answers are x equals 2, x equals 10, and x equals negative 10, right? Now, this question says, or what we're looking for in this question is the number of units produced in order to give a total cost of that amount, right? Obviously, we can't produce a negative number of units. So this one wouldn't make sense in the context of our problem. So really what our answer choice would look like, and the correct answer for this problem would be x equals 2 and x equals 10. Those would be your two answer choices I'd be looking for. Now, you're wondering how it can cost me $120,000 to produce 2 items and how it can cost me $120,000 to also produce 10 items. If you've ever ordered anything in bulk, a lot of times what will happen is if you're only ordering a few, they'll cost more per unit to order those few. But if you go to order a bunch of them, the cost per unit's a lot lower and it can kind of equal itself out. So here, two answer choices. So now we're going to go into chapter 6.2. Okay, first example, I have this chart here of age and years and millions working full time here. Okay, so A says find a cubic model that gives the number of Americans working full-time, Y, as a function of their age, X. Report using 3 significant digits. Okay. B says graph the unrounded model on the same axis as the data and comment on the fit. C says use the model to estimate the number of Americans working at age 59. Okay. So if I come over here to my calculator, I will enlarge it. What I have done is I've already typed my list in so that you don't have to sit here and watch me type it through. So to do that, you hit Stat, Edit, go to your list. So list 1 is going to be your X, list 2 is going to be your Y. Okay. Now what we're going to want to do is we're going to make sure your stat plot's on. So go second stat plot. So right now our plot's off. I'm going to turn it on. And make sure your scatter plot's the one that you have highlighted. Okay. Now I'm going to go zoom, and then I'm going to go stat. We can see our data here. Okay. Now I'm going to go stat, calc, and it wants us, in our problem, it says it wants us to do a cubic model. So I'm going to scroll down to cubic regression, number 6. Okay. I'm going to store it in our Y1. Okay. And then I'm going to hit calculate, and it finds it for us. Okay. The important thing to note here is it wants 3 significant digits. Now the first one is an e to the -4. Okay. So you have to move your decimal 4 places to the left. Let's go ahead and write out this cubic model right here. Okay. So I'm going to do the best I can for you to write it out. So if we took it from the calculator, wrote it on the board, because that was a little easier than writing it on the paper with the tools that I have. You get y equals -0.000362x to the third plus 0.0401x squared minus 1.39x plus 21.7. Okay, so that's what it would look like. Have it right here on our calculator as well. You should be able to follow the formula they give you right here and go straight and plug these in. The biggest thing is if it has an e to the negative whatever, I have to move my decimal 3 places or 4 places to the left, depending on whatever the number is here. Alright, now if I look at the graph, it does a pretty good job of estimating here. You can see it it's not perfect, but it does a really good job of getting really close to most of them. Okay, so B said we need to graph the unrounded model on the data and comment on the fit. I think it has a good fit. I think it's a pretty good fit. It's not a perfect fit, but it's a good fit. Obviously, I tried to write all that on that line before and it wasn't working, so I took it to the board instead. Let's look at C. C says use the model to estimate the number of Americans working at age 59. Okay, so at age 59, value 59. So all I did was do second calc value, x equals 59. So my y here is going to wind up being 4.99776645. So approximately, if we rounded it to 3 decimal places, it would be 4.998. Okay. 4.998. Okay. And if it tells you to round to however many decimal places, just go ahead and do what it tells you to do. But that is our answer for example 1. So we had our function, we wrote it on the board, we didn't wind up finishing it here, so don't pay too much attention to that. We put it on the board, had a good fit, and at age 59 we expect 4.998 million to be working full time. Easy enough. 2 says the number of U.S. adults with diabetes is projected to increase rapidly in the future. The projected numbers for selected years in millions are shown in the table. And we have the table on the next page. Okay, so here's the table. A says create a scatter plot of the data with x equal to the number of years after 2015 and y equal to the number of millions of U.S. adults with diabetes. So we're looking at the year after 2015. Remember that means that year 2015 is going to be year 0, so 2020 would be year 5, 2025 would be year 10, and on down here to 2050. So 2050 would be year what, 35? So make sure that you adjust your years accordingly, or you're going to get it wrong. B says create a linear function, C says create a cubic function, and D says graph the data on the same axis with the model to determine which is the better fit. So let's go to the calculator and do that. So what we're going to do here is we're going to create the scatter plot of the data first. What I recommend doing is going to your y equals here and clearing all your y equals stuff out that you had before. Okay. Then you're going to go stat edit. You're going to type your to-list in. I've already done it. Okay. Let me make this a little bit bigger so you can see it. So I cleared out my y equals, obviously. I did. Sorry. Didn't hit second. You don't need the second button. Second quit. Second quit. Just go straight to the stat button. Hit edit. And you type your to-list in here. I've already done that. Okay. If you want to see it as a scatter plot, now you can go zoom stat and it'll show it to you as a scatter plot, right? So what you see here looks almost like a straight line, right? So let's look at it. One of the things it wanted us to do, we've done the scatter plot, but B says create a linear function, C says create a cubic function that models the data. We're going to graph them both on the same axis, right? So pull it up. I do stat. If I want a linear function, we've done this, right? We're going to do second, our stat. We're going to scroll over to calc. We're going to do a linear regression. Okay. I'm going to store this one in y1. So I'm going to go vars, y-vars, y1. Okay. I'm going to calculate it out. So my function would be y equals 1.73, maybe 1.74x plus 40.51. Okay. So you should be able to take it from here, plug this in for A, plug that in for B, and get your function. Okay. We're this far along in the class, I shouldn't have to write that on the board for you every time. Okay. So when we graph it, it does a pretty good job, right? Now it wants us for part C to create a cubic function. So you should write the linear function right here that we just found. So y equals and whatever it was. Let's find the cubic function now. So if I go to it, I'm going to do stat calc cubic regression. Okay. I'm going to store this one so that we can see both of them at the same time. I'm going to store this one in y2 so we can look at them together. So vars, y-vars, y2. And I'm going to calculate it. And it gives you this function. Remember, it's got an e to the negative 4 here, so I have to move the decimal 4 places to the left here for my a before I put it in my function here. But you should be able to insert a here, b here, c here, and d here. Get this function and put it in right here as your answer for C. Okay. Now, the biggest thing is I want to graph them on the same data axis and determine which is the better fit. We've already seen that the linear was a pretty good fit. Okay. Here, blue one was our linear fit. Our red one was our cubic fit. Which one fits better? I was saying you might not think that a cubic in this situation would outdo a linear, but in this case it really does. Okay. The cubic hits almost exactly. The linear was off a little bit. Okay, so the one that I would actually choose in this situation would be the cubic function. So which one has the better fit? The cubic actually does in this situation. So just because you have a model that fits pretty close doesn't mean that's the best model that's out there. You can sometimes find a better model than what you have found. Example 3 says the percent of the U.S. population that were foreign born in selected years from 1900 and projected to 2020 are shown in the table. Okay, I believe the table is way down here on the next page. I believe this is the last question in the lecture for the year. How about that? So I'm going to type that in on my calculator here in a minute, but I'm going to go ahead and read through what A wants us to do. A wants us to create a scatter plot for the data using the number of years after 1900 as the input X and the percent as output Y. Okay, so the biggest thing to note here is X is the number of years after 1900. So if I'm looking at this, our initial X in 1900 is actually a 0. And then it goes 10. Then it goes 20. And then it goes 30, 40, on down, all the way to 2020, which would be year 120. Okay. So be careful inputting those in, and it doesn't go on an even pace. It starts by going years of 10, and then it actually changes here and eventually goes by ones. Okay, so keep that in mind as you type all this in your calculator. I'm about to type it in mine. I just finished typing mine in. If you need to take a pause here and type yours in, by all means do that. It takes a little while to get it in here. I didn't want you to have to watch me typing all that in. But remember what you have to do. So I'm just going to get out of mine, hit stat, edit, I'd clear out your old list first and then type your new list in. Remember, if you want to clear a list out, you go up to the top, you hit clear, and it clears the list out. Okay. So now that we have it in here, what it wanted us to do is it wanted us to create a scatter plot, number of years after 1990, and graph it. So what I'm going to do is I'm going to do zoom stat number 9, and it's got a nice graph of our scatter plot here. Okay. Now, B says find a cubic model or a function to model the data and graph the function on the same axes with the given data points. Okay. So if I pull it up, I can go stat, calculate, cubic regression. Okay. I'm going to store it in Y1. I've already cleared out my Y equals list. If you need to go back and do that, you can. Otherwise, it'll just override it. It won't be a problem either way. So, vars, Y vars. I'm going to store mine in Y1 and calculate. And it gives you the function there. So, if you needed to write this particular function down, you would have to move the decimal 6 places to the left for your A, 4 places to the left for your B, and just plug them all in. Okay. Now, let's look. Y'all are capable of writing this function now. So, just look and see how it fits. That's a terrible fit. Right? I don't think that does well at all. Alright. So, instead, let's find a quartic function to model the data. Okay. So, if I go stat, calc, quartic rig. Okay. I'm going to store this one. Alright. In Y2. Okay. Calculate it. If you needed to write it down, you could. It just goes a x to the 4th, b x to the 3rd, c x squared, dx, and then plus e. And you could type all these in. No problem. If I hit graph to compare them, the blue one was the first one, the red one's the second one. The red one does a very fine job of getting really close to most points, right? Does a really, really good job. So in this case, I believe the next part says, use the graph to determine which is the better fit. Obviously, the quartic, in this case, is the better fit. Now, this is the very last thing of the semester, so I'm going to use it to kind of showcase a few things you could do with this information you just learned. So now you have a scatter plot of this data. We found cubic, we found quartic. If you wanted to, you could find a couple other ones, okay? If you wanted to find quadrig, let's find quadrig. Okay, I'm going to store this one in Y3. Function Y3. Okay. Calculate it out. Finds it for us. Okay. So this is just an x squared function. So if I graph it, I don't expect it to fit very well. There's the first one. There's the second one. There's the one we just tried. It's not much different from the very first one we found, right? So if I wanted to, I can say, okay, well, that one didn't work. I want to try to find something that's better than this quartic regression. I don't know which one to use, but if I wanted to, I could try a natural log regression, I could try an exponential regression, I could try a power reg, and I think that's all the options. You could try sine reg if you wanted to, although sine and cosine aren't something we do in this class. You could go through all these options and do each and every one of them to see which one fits the best, right? So if you did a natural log regression, I'm going to save it in Y3 as well, because that last one didn't work very well anyway. So y-vars function Y3. See if it does any better than that squared function. Calculate it. Doesn't allow you to do it. Well, how about that? So, it says you need 3 data points for that one. So, let's not do that one. So, let's go. That one didn't work. Let's see if we can get another one to work. Sometimes you have that when you try to do regressions and you're just trying to choose random one. Let's see if exponential will work. I don't know if it'll work either. Might have an issue as well. Haven't tried these yet. Let's store this in Y3. See if it'll calculate it for us. It might not. It might have an issue where it can't calculate it for us. It happens. That's why we go through and you can try all of them. It doesn't take a lot. The calculator does most of it for you. Okay, finds it for you. It's in Y3. See how well it does. There's the first one, obviously. The second one, which did the best. The third one does not do worth a darn, right? So we can come through here and we can keep trying these if we want to. I think we found the best one so far. Let's see if you wanted to try a sine one. Okay, even though we don't do that, let's not worry about that one. That's really not this class. I'll get in trouble if I go too far. But if we look at the graph, clearly the one that works the best was our quartic regression. Like I said, you now have all these options at your fingertips, though. If you do have data, you can find a function that fits it, and you could try several different functions and pick the best one. That's the biggest thing to get out of this. I've appreciated y'all this semester. Thank y'all for having me. Thank y'all for having me this semester. Thank y'all for working hard, making it to the end. If there's anything that you need help with before this test 3, before the final, please let me know so we can get it worked out. Utilize your calculator whenever you can to help you figure stuff out. You know, I push for that a lot and try to show you the easy ways to do it on the calculator. If you can do it on the calculator, like I said, if you have any questions, please let me know. Really appreciate everybody working hard and paying attention this semester. Feel free to reach out to me. I'm going to try to get your grades uploaded so that you can see what you have before the final exam, so you'll know what you need to make to get whatever grade it is in the class that you're shooting for. Other than that, thank y'all. Good luck next semester. Take Stat 201. I'll be there for you. If you like my class. If you didn't like my class, fair enough. Try it with somebody else. There's plenty of other good teachers at this university. So, y'all have a good one, and I will, I guess, be communicating with you about the upcoming test and the final.